Okay, in the next section we need to look at the evidence which supports the special theory of relativity. The first thing is to discuss muon decay as experimental evidence to support this. In the atmosphere, we have these cosmic rays that come into the upper atmosphere, and then they tend to decay and break into all fantastic kinds of different particles. One in particular is called the muon, and you can tell it because it's got a mu sign here. Mu, there's a muon, there's a negative muon there, and so on. And they're made in the upper atmosphere, and they're able to come basically all the way down to Earth. So they have enough time in their speed that they travel at to reach the Earth. So, and this, the only reason they can do it is because of this relativistic effect, which is time dilation. So why is the muon decay, the observation of muons at the surface of the Earth, evidence to support special relativity? Muon decay are made in the atmosphere, and they basically fall 10 kilometers to the Earth and decay usually in that time. So the half-life of a muon is around 2.2 times 10 to the negative 6 seconds. That's proper time, which means the muon is basically static with respect to its clock. And we know that muons fall down at 99% of the speed of light. So how long would that take? Well, it's pretty straightforward. The time is the distance divided by speed. The distance is 10,000 meters divided by pretty much 3 times 10 to the 8, or 1% from that. And the time is 33.3 times 10 to the minus 6 seconds. But hold on. We've already said that the half-life is 2.2 times 10 to the minus 6 seconds, and this is going to be 15 half-lives. There's going to be next to no muons left, yet we observe many of them. We know that they're surviving this travelling through the atmosphere. There should be almost no muons left, but there were many. And what is the reason for that? Why is it that this event that should have killed, basically finished all the muons, and is still existing after this time? Because for them, it is not this time. For them, they have travelled for less than this time. Their clock is going slower than ours. So the muon's measurement of time is much slower than ours. So this is proof of the special theory of relativity. So the number of muons which arrive at the surface of the Earth is much higher than it should be, and many less than have decayed than expected. Now the muon's clock, the clock that's at rest relative to the muon, is going slower than ours, and it's the muon that measures proper time. So this is time dilation. We measure it as being, it's like the sandwich. We measure a 3-minute sandwich as taking 5 minutes. We measure the proper length, which is the height of the atmosphere, because the atmosphere is at rest relative to us. So the muon measures a contracted length. And we must agree on speed, because we both agree on what the speed of light is. It basically takes it less time. There's less time that's passed, and it's also a shorter length. So basically, it doesn't violate this fact that we must both observe the speed of light as being the same constant. So this is a support of the special theory of relativity. This was discussed in an exam paper, 4 marks. The observations of muons created in the upper atmosphere of the Earth are used as evidence for time dilation, and discuss this. And these are what was expected in the mark scheme. We can solve a problem. This is from November 2006. A particular muon is created in the upper atmosphere and has a lifetime of 2.20 microseconds, as measured in the muon's frame of reference. The speed as measured by an observer is 0.995 c. In other words, the gamma factor, the Lorentz factor, is 10. Calculate the distance moved by the muon during its lifetime as measured by an observer on the ground. Now, we're going to have different ideas of what the time is. The proper time is 2.2 microseconds, 2.2 times 10 to the minus 6. And we've got a factor of 10. So I'm going to basically measure my time as being different from his. So my measurement of time is basically going to be 10 times as much as his measurement of time, because his measurement of time, t0, is the proper time. So it's 2.2 times 10 to the minus 5 seconds, 10 times as long. And so what is the distance? The distance is equal to speed times time. The speed is still the same, 0.995 c. We're both going to agree on that. So then we can work out the distance from that. The next thing is this idea of the luminiferous ether. This is a substance that permeates throughout the universe, which is basically the standard frame of reference. And light, when it travels, was supposed to move relative to this luminiferous ether, in other words, move relative to this frame of reference, but we weren't sure which way it was going. It's called the ether drift. If it was going in the direction the Earth's going against the direction of the Earth at 90 degrees. So it's a bit like sound in a way. Sound travels relative to the medium in which it is placed. What is the ether? What is a substance through which light travels? What is this ether? What is this thing that supports light, this medium that the light travels through? So it was believed that the Earth was orbiting the Sun and cutting through this luminiferous ether, but we didn't know which way it was going, which way was the luminiferous drift. So they did this experiment, Michelson-Morley. This is a famous experiment where he had this device where he shone light from here. This is a semi-silvered mirror. So some light is reflected off here and comes down and is observed in this telescope here. And then there's another beam of light which goes through this one, reflects off this mirror and comes here. Now, depending on the speed of light, you're going to get different times that they're going to travel here. We can use one of these mirrors can be adjusted to make sure you can get basically an interference pattern, because the light reflects off there and interferes with the light that gets reflected off here. So you would expect to see an interference pattern due to the different paths of light. So this apparatus travels on the Earth through the ether, and we wanted to find what is the direction of the ether drift, what is the absolute frame of reference. And then you repeated this experiment, rotating it by 90 degrees, and you should get different readings. You should get a shift in the interference pattern. So you'd expect one path to be a little bit slower because it's moving against the speed of light. So the interference fringes should move. It was believed that light travelled through this medium called the luminiferous ether, and therefore they expected this interference pattern to change. But the actual results were there was no change in the interference pattern, so it didn't matter which direction you were travelling in, it was still the same number of wavelengths and the same time, because it happened in the same point in space, and therefore the speed must be the same. So the conclusion supported Einstein's idea, which there's no absolute reference frame. So remember, one of the postulates is that there's no absolute reference frame, and all the experiments done in one frame of reference, inertial frame of reference, will give the same results as in another frame of reference. And there's no ether, and all observers measure the same speed for the speed of light. Another one, an evidence, is this is the speed of light in a vacuum is independent of its source. You should be familiar with this pion decay. And this is the experiments involving the observation of fast-moving pions into two gamma-ray photons. A bit of maths for you. The rest mass of a pion is 135 mega-electron volts per c squared. It's got a half-life of 0.16 e times 10 to the minus 16 seconds. What it does, it decays. It decays into two photons, and these photons are gamma photons, high-energy photons. So you need to be able to calculate the energy that's in these photons. You basically start off with rest mass, 135 MeV per c squared. You turn it into energy, You divide the energy by 2, and you basically get the energy per photon for each of these gamma rays, and then knowing the speed of light, you can work out the frequency. Where are these pions observed? Now, they're known as gamma ray bursters, GRB, which are observed in the universe, in particular coming from neutron stars. We know neutron stars are a source of lots of radiation, and this is thought to come from the rapid collapse or rapid expansion of neutron stars. I've shown you these two gamma photons there and there, which haven't been aren't released from the neutron yet, but I'll show you. What's going to happen is that this neutron star is going to rapidly expand. It will send one photon in this direction, and then also this photon on this side from this direction. But this outside of the star will be expanding very rapidly, so really it will be moving away from this outside part of the star, which is already moving to the right. We are going to be on the far left hand side, and we're going to observe these two photons. So suddenly there's a sudden expansion. The first photon was sent from the side of the star that was expanding towards you. The other one was sent from the side of the star that was expanding away from you. So really, would we observe if the speed of the gamma photon depended on the speed of the source? The one that was moving towards us to start with would have the speed of light added to that. The part of the star that was already moving away from us, the speed of light would be subtracted from that. We know that the time is the same. What we found was they arrived at the same time. They travelled pretty much the same distance, therefore they must have the same speed. So in other words, the photon left the surface of the star. It didn't matter how fast the surface of the star was moving at that time, the photon still moved at the same speed, no matter what the speed of the star was. So basically the speed of the photon, the speed of that radiation, is independent of its frame of reference.